Hello everyone, welcome to this lecture on operations on relations. Just to recap, in the last lecture we introduced the definition of relations and we saw various types of relations. The plan for this lecture is as follows. We will see various set theoretic operations which we can perform on relations. Specifically, we will be discussing on the powers of a relation and closure of a relation. So, it turns out that since relations are nothing but a set, but so we can perform various set theoretic operations like union, intersection, set difference on relations as well. So, to demonstrate this, let us consider two relations R1 and R2. You have a relation R1 which consists of all x comma y pairs or all real numbers x comma y where x is less than y. So, here my relation R1 is defined over the set of real numbers, my domain is the set of real numbers. So, and R1 will have all tuples of the form x comma y where x real number x is less than real number y. And similarly, my relation R2 is another relation defined over the set of real numbers consisting of all x comma y pairs where the real number x is greater than the real number y. Okay. Now, if I take the union of these two relations, and the union of these two relations is well defined because both R1 and R2 are sets and we can perform the union of two sets. So, it turns out that the union of these two relations will have all pairs of the form x comma y where the real number x is not equal to real number y, okay, because the union will have all the elements of R1 and the union also will have all the elements of R2. So, one way of describing the union of the two relations is that it have all x comma y pairs where either x is less than y or x is greater than y. But if we want to represent the same, if we want to state the same thing in a compact way, we can say that it has all x comma y pairs where x is different from y. Whereas, if I take the intersection of these two relations R1 and R2, then it turns out to be an empty set because you can't have real numbers x and y where x is simultaneously less than y as well as x is simultaneously greater than y. So, you can't have any x comma y pairs satisfying simultaneously the conditions for the relation R1 and R2. In the same way, it is easy to see that if I take the difference of the relation R1 and R2, that means if I subtract R2 from R1, then I will be getting the relation R1. Namely, it will have only the elements of the form x comma y where x is less than y. And similarly, the difference of R2 minus R1 will be the relation R2. Okay. Now, we can perform another interesting operation on the relations which is called as composition of relations. So, imagine you are given two relations R and S. The relation R is from the set A to B. So, R is a subset of A cross B, okay, and your relation S is from the set B to C. So, S is a subset of B cross C. Okay. I am taking here three arbitrary sets A, B, C. A, B, C may be same, they may be different, there is no relationship, they are just arbitrary sets here. Okay. And I am naming the elements of set A as A1 to AL. Similarly, the elements of B are named as B sub 1 to B sub m and elements of C are named as C sub 1 to C sub m. Okay. Now, the composition of these two relations is defined as follows. So, first of all we use this notation SOR, okay, and this means that I am going to apply the relation R first and then the relation S. Okay. So, it is not the relation S applied first and then the relation R. We are going to apply the relation R and on top of that we are going to apply the relation S. Okay. So, this will be a relation from the set A to C, okay, and that is why this ordering matters a lot. So, if I am saying S composed with R, so this operation O is called as the composition operator here. And right now I am composing the relation S with the relation R. If I write ROS, then that is a different relation. That means I am composing the relation R with the relation S. That means here S will be applied first and on top of that the relation R will be applied. So, the notation specifies clearly which relation is composed with which relation. So, this S composition R will be a relation from the set A to C. That means, it will have pairs of the form ordered pairs of the form A comma C, and the definition here is it will have all ordered pairs of the form A comma C provided you have some element B small b in the set big B such that A is related to B as per the relation R and B is related to C as per the relation C. So, pictorially if you have say AI related to Bj as per the relation R and the same Bj is related to Ck as per the relation S. Then we will say that AI is related to here it is Ck, AI is related to Ck as per the relation S composition R. Okay, so, it is some kind of transitive property here that or transitive pairs or transitive tuples of the form A comma C which we will be including in the relation S composition R. Okay. So, once the definition of compositions of relations is given, we can define what we call as powers of a relation and how it is defined. So, imagine R is a relation from A to B, that means R is a subset of A cross B. Then the definition of powers of a relation is as follows. So, R power 1 is defined to be the relation R itself and then recursively I define the n plus 1th power of R to be the composition of the relation which is nth power of R with the original relation R. So, again I stress here the order matters here. The n plus 1th power is defined to be the composition of R power n with R, that means you have to apply the relation R first and then you have to apply the relation R power n. It is not equal to, it need not be equal to the composition of R with the nth power of R, that may or may not be the case, because in general the composition of two relations need not be commutative. Okay. So, let me demonstrate the powers of a relation with an example. So, here I have defined a relation R consisting of the pairs 1 1, 2 1, 3 2 and 4 3. So, R power 1 as per my definition will be the relation R itself. Now, R square will be the composition of R with R and my claim is that R square will consist of these 4 pairs. Why so? So, let us start with 1 comma 1. So, you have 1 comma 1 present in R and the same 1 is again related to 1 itself as per R. Therefore, I can say that transitively. So, this is your A here, this is your B here and this is your B here and this is your C here. So, as per the definition A comma C should be there in R square. So, that is why 1 comma 1 will be present in R square. Okay. Now, take the tuple 2 comma 1. So, this is your A comma B and you have the tuple 1 comma 1 also present in R. This is your B comma C. So, therefore, A comma C should be in R squares, that means 2 comma 1 will be in R square. If you take 3 comma 2 present in R, okay, so this is your A, this is your B and you have 2 comma 1 present in R all as well. This is your B, this is your C, therefore, A comma C namely 3 comma 1 will be in R square. And in the same way you have A comma B here namely 4 3 and B comma C here namely 3 2, that is why 4 comma 2 which is A comma C will be present in R square and no other tuples will be there in R square. Okay. That is how we take the powers of the relation. If I want to compute R cube, then it will be the composition of R square with the relation R. So, I will take this R square here first and compose it with the original relation R. That means, the relation R has to be applied first and then on top of that the relation R square has to be applied. Okay. So, for instance, this is your AB here present in R and you have BC as well present in R square. Therefore, AC which is 1 comma 1 will be present in R cube. Similarly, 2 1 is present in R and you have again 1 1 present in R square. So, that is why 2 1 is present in R cube. You have 3 comma 2 present in R and 2 comma 1 is present in R square. So, that is why you will have A comma C which is 3 comma 1 here present in R cube. You have 4 comma 3 present in R and you have 3 comma 1 present in R square. So, that is why 4 comma 1 is present in R cube. And similarly, if you take the R power 4 relation, then it turns out to be the same as R cube. And now you can check yourself that after the fourth power you take any power of the relation R, it is going to give you the same relation as R cube. You will not get any new tuples added in the relation R in the next powers of R. Now, next what we are going to discuss is a very nice interpretation of the powers of a relation in terms of a property in the corresponding graph. So, imagine you are given a relation over some set A consisting of n elements and suppose the relation is represented by a directed graph G. Now, the claim here is the following: the ordered pair AI AJ will be present in the mth power of the relation, namely AI is related to AJ in the mth power of the relation if and only if there is a directed path of length m from the node AI to the node AJ in the digraph of your relation. Okay. So, what do I mean by directed path here? So, remember G is a graph where you have vertices A1, A2, AI, AJ, AN and you have directed edges. So, if there is a direct edge between two nodes from one node to another, say from A1 to A2, then this will be considered as a directed path of length 1. Whereas, say if you have a path of the form from A2 you have an edge to A1 and from A1 you have an edge to AN, then I will say that the path A2 to A1, then I will say that the sequence of edges A2 to A1 and A1 to AN, this will be considered as a directed path of length 2 from A2 to AN, right. Like that you can imagine a directed path of length m from AI to AJ. That means, your source or the starting point will be AI, the end point will be AJ and intermediate and you will have m number of intermediate directed edges, okay, in that path, right. That is the interpretation of a directed path. Later on when we will discuss graph theory in detail, we will formally define what exactly is a path, path length and so on, right. But right now we want to prove this nice theorem regarding the power of a relation. And since this is a universally quantified statement, because even though the universal quantification is not explicitly available here, but the statement is for all m greater than equal to 1. So, that is why we will use a proof by induction on the power m to prove this theorem or a property, and the base case will be m equal to 1, and the statement is of course trivially true for the base case, because if at all AI is related to AJ in R, that means that there will be a direct edge from the node ai to the node aj in my graph. That comes from the definition of the digraph. So, the base case is trivial to prove. Now, assume that my inductive hypothesis is true, that means I assume that the statement is true for m equal to k. By that I mean that if ai is related to aj in the kth power of the relation, then there exists a direct path, there exists a directed path, not direct path, there exists a directed path of length k starting at ai and ending at aj in the graph G. Okay. Now, I go to the inductive step and I consider an ordered pair, an arbitrary ordered pair in the k plus 1th power of the relation. So, suppose the ordered pair ai aj is present in the k plus 1th power of the relation, and the k plus 1th power of the relation is basically the composition of R with the kth power of the relation as per the definition of powers of the relation. Now, when can it be possible that ai is related to aj in the k plus 1th power of the relation? That is possible only if the following two conditions hold. There should be some element a such that ai is related to a, and that element a should be related to aj. Then only I can say that ai is related to aj in the k plus 1th power of the relation. But ai related to a means there is a structure of this form in your graph, namely there is a direct edge from ai to a. Okay. So, this should not be a dotted arrow, this should be actually a straight arrow, because indeed I have a direct edge from ai to a, and the interpretation of a being related to aj in the kth power means I have a directed path of length k starting at a ending at aj. This comes from my inductive hypothesis. Now, what can I say regarding a path from ai to aj? I can say that if I concatenate these two paths, that means if I take the edge from ai to a first, and then once I reach the node a, from there I traverse through this path and come to the node aj, that will give me a path starting with ai ending with aj. And now, what can you say about the length of that path? The length of that path will be k plus 1. That means, I have shown here that if the ordered pair ai aj is present in the k plus 1th power of the relation, then in the directed graph of your relation you indeed have a path of length k plus 1 starting at ai ending at aj. Okay. Next, let us define what we call as closure of a relation. So, what do we mean by this? So, imagine you are given a set A, okay, that may be finite or infinite, and you are given a relation R over the set A. That means, the relation R is a subset of A cross A, and I have some abstract property P. It is some abstract property, and I am interested to check whether the relation R over the set A satisfies this property P or not. If it satisfies the property, well and good, but that need not be the case. R that is given to you need not satisfy the property. So, the closure of the relation R is defined with respect to this property P. Okay. So, if you change the property P, the closure will change. So, what exactly is the closure of the relation R with the property P? Well, it is a smallest superset of R which has the property P. So, pictorially what I am trying to do here is I am trying, if my relation R already satisfies the property P, I do not need to add anything to the relation R, I do not need to add any extra element to the relation R to satisfy the property P. But if my relation R does not satisfy the property P, then I will be interested to introduce new ordered pairs in the relation R and convert it into another relation S, so that the expanded relation S satisfies the property P. That is what I am trying to do here. So, this S you can imagine as expanded version of R, and this S is also going to be a relation over the set A itself. I am including the original relation R, that is carried as it is. On top of that, I am adding, I may add few extra elements and try to ensure that the expanded R, which is S, satisfies the property P. But I am not going to do the expansion arbitrarily, I am interested in the least possible expansion. Okay. Least expanded version. What I mean by least, that means this is the minimal expansion which I need to do in order to ensure that the relation S satisfies the property P. That is important. Otherwise, what is a big deal in expanding the relation R? You keep on adding any arbitrary number of elements, definitely you will more or less soon get an expanded version which will satisfy the property P. So, we are interested in the smallest possible expansion. So, let us see some examples of this abstract property P and how the resultant closure looks like. So, my first abstract property is the reflexive property, and this gives us what we call as reflexive closure of a relation. So, you are given a relation R over the set A, and I am interested to see whether this relation R satisfies the reflexive property or not, reflexive over the set A. Okay. So, that is what is the reflexive closure of the relation R. So, how can you construct a reflexive closure of R? Well, you just take the union of R with all ordered pairs of the form AI comma AI, where AI is present in your set big A. If your AI comma AI is already there in the relation R, then as per the union definition you will not be including it again. Remember, union means if AI comma AI is present in R as well as in this new set, new relation, right. So, this new relation I am calling it as delta relation. So, this delta relation you can imagine it is consisting of all ordered pairs of the form AI comma AI such that AI is present in A. So, if AI is already there in R, it will not be included again, but if AI is not present in R, then due to the union, due to taking union with this delta, it will be now added to the relation R, and now you can see that this is your expanded R. Okay. That may be same as R itself. In case if your relation R is already reflexive, then you are not going to add any extra elements. Okay. So, this expanded R will have the original elements of the relation R plus this expanded R will satisfy the reflexive property. Okay. Now, let us take the case when my abstract property P is the symmetric property. So, again I am given a relation R defined over the set A, and I am interested to form a symmetric closure of R. Why I am calling it closure? Because I am trying to put a layer over and trying to enclose the original relation R and get a relation which has the original R as well as it satisfies the property P. That is why it is called a closure, right. So, how do I form the symmetric closure? So, if you recall the property of symmetric relation, then the requirement there is that if A comma B or if AI comma AJ is present in R, then I need that I need the guarantee that AJ comma AI should also be present in R, right. This is the requirement from a symmetric relation. So, and I need to include the original relation R. So, what I am going to do is I am going to take the union of R with what I call as the inverse of the relation R. So, this is the inverse relation, and what is this inverse relation? It is defined to consist of all ordered pairs of the form AJ AI such that AI is related to AJ in the original relation. Okay. So, if in your original relation AI is related to AJ, then in the R inverse relation AJ will be related to AI. And it is easy to see that if you take the union of R with its inverse, then the resultant relation will be symmetric and it will have the original relation R, and this will be the smallest possible expansion of your relation R, which satisfies the symmetric property. Okay. Now, what about the transitive closure? So, it turns out that finding transitive closure is not that simple. Why so? So, let me demonstrate that with an example. So, you might say that intuitively to find the transitive closure, I add all elements of the all ordered pairs of the form A comma C, such that, again sorry for the typo here, such that A is related to B as well as B is related to C in the relation R, because only when I add such ordered tuples of the form A comma C in the relation R, it will ensure that the transitive property is satisfied. So, let us try to do that. You are given the original relation R, and I am taking the union of the original R, and I am adding all the ordered pairs of the form A comma C, which are needed to ensure the transitivity property. So, for instance, I need to add 1 comma 2. If you are wondering why I need to add 1 comma 2, because I have A comma B present here, I have B comma C present here. So, I need A comma C, which is 1 comma 2 also to be present, which is not there in R. So, I say let me add it. In the same way, I have 2 comma 1 present, which is your A comma B, and you have 1 comma 3 also present, which is B comma C. So, you should add 2 comma 3 and so on. So, these are the new things which I add, and my R prime will be this new relation. Okay. It has my original relation R, but now let us stop here and ask whether R prime is transitive or not. It turns out that R prime is not transitive, right. So, for instance, you have 2 comma 3 present here, which is your A comma B, and you have 3 comma 2 present, but you do not have A comma C, namely 2 comma 2 present in the relation R prime. So, even though you have expanded R and got R prime, your R prime is not satisfying the transitivity relation property. So, what you can do is you can again apply the rule, and to apply the rule, what I do now is I take the union of R prime, namely the expanded R, and add all the extra ordered pairs of the form A comma C, which were missing in R prime to satisfy the transitivity property. So, see, I am adding 1 comma 1 here. Why I am adding 1 comma 1? Because I have A B here and B C here, but A C, namely 1 comma 1 is not present in R prime. So, I am adding here and so on. And now, I call this expanded relation as R double prime, and now you can check that this R double prime is indeed satisfying the transitivity property. So, if you see closely here, what happened in this whole process is the following. First time when I expanded the relation R, I took the union of R with all the tuples which will be present in R square. You can verify that as per our definition of R square, the tuples which I have highlighted here are nothing but R, which are the tuples in R square, are the tuples in R square, sorry. So, the tuples which I have highlighted here and I have added with the tuples which were present in R are nothing but the tuples of R square. In the same way, when I expanded R prime to R double prime, the tuples which I added actually are nothing but elements of R cube, and recall R cube is nothing but R square composition R and so on. So, it turns out that when we want to find a transitive closure, it need not be a one step process. I need to apply this rule, namely keep on adding the ordered pairs of the form A C such that A B and B C are there in your expanded relation, and I may need to keep on applying this process several times, and then only I can obtain the transitive closure. Okay. So, that brings me to the end of this lecture. Just to summarize, in this lecture we introduced some set theoretic operations on relations, and we discussed the various closure properties with respect to a given relation. Thank you.